Okay, now let's turn to looking at how we get the perspective matrices and use them in the same pipeline that we used our orthogonal matrices. What we'll see is that in fact we get a much more general case because when we did orthogonal matrices, our standard orthogonal matrix did not include the oblique projections, and we sort of had to tack that on in the end. It turns out in the standard OpenGL fixed function pipelines, there were two versions of perspective projection. One which was very general that included the equivalent obliqueness in a perspective projection, and then one that was more symmetric that corresponded to an orthogonal projection for the parallel projection case. But let's start again with the simple perspective that we examined before and then try and generalize it. So we said, if we start with the same argument and say, well, look, let's forget about the pipeline for a minute and say, before what we said is a real simple problem when you're doing orthographic projections is to have a box whose corners are at 1, -1, -1, -1, and 1, 1, 1. And that's a really nice box because clipping becomes very easy because all you have to do is check whether x, y, and z are greater than or less than -1 and 1. So it's a very nice, easy volume to work with. Well, what's the equivalent for perspective projections? Well, we said before that we tend to put our center of projection to start with at the origin, and then the projection plane cannot be in the plane z equals 0, and so we tend to say the camera is over here and we're looking forward, and for a normal perspective projection, the near plane will be in front of us, as will be the far plane, and the far plane will be further away than the near plane. Actually, what a lot of systems let you do, if you just look at the mathematics, that anything in the plane z equals 0 is going to cause the equations to blow up because you'll be dividing by 0. But in fact, if you put something back here, it will project, but notice because these projectors go down below y equals 0, things will be flipped over. So some systems will actually give you the projections of things behind the camera, although it makes more sense in a physical world to say, no, we only want things that are in front of the camera, so you have to have the near plane in front of the camera. Although as I said, certain systems will not enforce that restriction on you, and you can get some pretty interesting looking projections. But let's just take this picture and say, hey, okay, here's the simplest case. I'll say that the near clipping plane has its bottom left corner at -1, -1, -1. It's in the negative z half space, and the top right corner is at 1, 1, -1. And then what do the sides look like? Well, the sides now are defined by the planes x equals z, x equals minus z, y equals z, and y equals minus z, and they go off at a 45-degree angle. Here, if you were to measure this angle over here, it'd be 45 degrees. So that's a pretty simple one to work with if you're going to directly work with perspective. Also note, you get a very interesting thing here with perspective, that this far clipping plane is totally free in the sense that all these specifications define this pyramid, or actually this frustum, because I'm going to cut it off here, but I can let the far plane, I can let z equals minus far pretty much be wherever I want, and it won't come into the specifications that I need to make this volume, which is kind of interesting. We'll see that come up, and it gives us a little more freedom in how we do things. Okay, so let's look at the perspective matrix for that, and it turns out to be very, very simple. This is kind of what we had before when we did simple projection. We said here's a projection matrix. If we do perspective division, then we get the standard equations for perspective. But notice, again, as with all projection matrices, if they really do the projection, we lose a degree of freedom, and we see that here in the matrix because we have this column of zeros, and so the determinant must be 0. Once again, what we're going to do is delay the singularity, the forming of a matrix that doesn't have an inverse till the very end. So what I'm going to do is look at a generalization that doesn't lead me to lose everything along a given projector to lose its distance along that projector. So look at this generalization here. I'm going to put in two constants here, alpha and beta, and I'm going to have the -1 here because I really need something here for this really to be a perspective projection. And in fact, if you do that, actually here's a simple way to see what I'm doing, is take a point xyz1 and look at what happens after I multiply by this matrix. I get first I get x prime equals x, y prime equals y, z prime equals alpha z plus beta, and w prime equals minus z. Now, if I do what I have to do eventually, which is now divide by z in order to get back into three-dimensional space, I get an x double prime, y double prime, z double prime, and I just divide by this minus z, and here I get my standard equations for projection. Now, what's different here is because I put in two parameters, alpha and beta, I now can play with them in order to get some other flexibility in what I'm doing, or to fix some other conditions. And the conditions I want to pick are ones that will help me when I'm trying to do hidden surface removal, because the point of using this non-singular matrix here is that I preserve distances. So if I pick alpha and beta to be the following, I'll give you the answer here. You know, you can derive this in many ways. If I give you the following alpha and beta in terms of the near and far distances, what that will do is map the near plane to -1, which is kind of what I want. Let me go backwards, which is what I want over here. It's going to map that near plane to -1, and it's going to map the far plane to +1. So that gives me this volume here with far pushed up to +1. Now that's really interesting because it does a couple of other things. Because look at what happens over here. It takes the side planes, x equals z, x equals minus z, and converts them into the planes x equals 1 and x equals -1. Likewise, for z, it converts that to y equals +1 and y equals -1. And because it moved these two planes in z to -1 and 1, what you've done is you've distorted everything with this matrix, so everything fits inside of this cube again, which our standard cube, which goes from -1, -1, -1 to 1, 1, 1. Hey, I just got back exactly what I did all that work to do in the orthogonal space, and here I did it for a much more complex problem, because if you come back again over here, this is nonlinear. We're getting this, and this is what perspective does. It gives us this diminution of size by dividing by the z. But later, when I get rid of the z, I have exactly what I want, which is the x's and the y's, which are in a simple perspective. So this is everything that I want. It's very surprising to me result. If you look at the picture now, which is kind of equivalent to the picture that we had when we did this for oblique projections, you get the following. If here's again a top view of our projection, you see this line that corresponds to the plane x equals z. You see this line here corresponds to the plane x equals minus z, or z equals minus x. Center of projections here at the origin. Here's the near plane, here's the far plane. We apply that transformation, and what it does is it distorts the object. But it distorts it a little differently than in the orthogonal case. It takes things further away, and those things further and away, it sort of compresses them in planes of z equals a constant. So the distance here for this cube I'm looking down on is smaller because it's further away from the viewer, and the distance down here is longer. So I have a distorted object, but now again, when I do the orthogonal projection of that distorted object, so say I'm going to project it straight down, I get exactly what I wanted from the perspective projection, namely that the back things further away are smaller, that's this compression over here, and things closer to me are normal, so it's doing the operation. Or in other words, I'm doing a normalization step followed by our orthogonal projection, exactly as I did before with our oblique projections. And again, the clipping volume has become this really nice clipping volume, which is exactly what I want. The clip coordinates, I've converted that into the planes x equals 1, x equals minus 1, y equals 1, y equals minus 1, z equals plus or minus 1. Now, the only little thing I'm missing here is I did this for this problem where the near plane was at z equals minus 1 and the far plane was anywhere. So I did this for a very, very special case. Or, and more importantly, I did it for the special case where the sides started off at 45 degrees for the original viewing pyramid. So now I have to do kind of what I did before. I have to do the scaling in order to say, well, what if I gave you different sides and different values? Or the way I would do that would be to give you this corner and give you left, right, top, bottom in this front plane, and near and far. So now I have to do some scaling and translation to get me into this form. And once I have this form, I know that that normalization will work very nicely. So let's go back ahead again, sort of summarize that. One of the real advantages of doing it this way, and it's crucial, is that you can show, although it's, mathematics is a little hard, by using that form with the alpha and the beta, which may have seemed kind of arbitrary to you. What I've done is I have now maintained distances. So if in the original perspective that I gave you, the original diagram, or let's say in the original space, if 2 points along a projector had z1 greater than z2, once I've done that transformation the way I've derived it, the transform values still maintain that order if it's within the clipping volume. If it's not within the clipping volume, you're not guaranteed to maintain the ordering, but I don't care because I'm clipping them out anyway. This means that hidden surface removal, when I've converted the perspective projection into an orthogonal projection, then the z's are in the right order, but the distances could be distorted. But we know that perspective projections distort distances. But all I'm testing for in the z-buffer algorithm is whether z1 is in front of or back of z2, if that's the z for a particular fragment. I don't really care how much behind it is or how much in front of it is. So this all works beautifully, and that's the way it's done. Okay, so now let's look at the functions in WebGL, which are the functions back in the old OpenGL fixed function pipeline. So there are two functions, GL-Frustum and GL-Perspective. Remember, GL-Frustum used min-max, or this would be instead of min-max, I probably should have converted them to left, right, top, bottom, near, and far, but those are the values that are in there. And the perspective function, GL-Perspective, is much simpler. Let me come back here. Where it gives you this angle, gives you this angle, gives you this angle and these the near and far and the aspect ratio. Now, the normalization if we do, let me back up, start again. Frustum is a lot more general than perspective. And the reason is that this pyramid you can get doesn't have to be symmetric. It could be skewed, and that's the perspective equivalent of obliqueness. In GL perspective, you get what's called a right pyramid, where it's symmetric going from left to right, and if you drew a line to the center here, from the center of projection to the center of the front clipping plane, it would be orthogonal. It's called a right pyramid or a right frustum. Okay, so if we look at the matrices that you get, how do I now derive the more general case for frustum? And I could argue in the following way, that because it has this obliqueness to it, that what you can do first is do a shear to get the obliqueness out. So that's the equivalent of what I did in the orthogonal case. So I do a shear to get this into a right pyramid. And then I do the scaling that I need to do to make this come out to be as it was for the orthogonal case. So that's what we're arguing here. The derivation is in the book. So you're going to wind up doing the perspective we had before, a shear and a scale in here. It turns out with the center of projection at the origin, you don't really need a translation to do this. Sort of the shear replaces the translation. Okay, so sort of summarize, I think it's pretty clear why we do it this way, because now I have a single pipeline that does both perspective and orthogonal viewing. I have the perspective division at the end, but because I'm building it all in hardware, it doesn't really matter if I have an orthogonal projection and we're doing the perspective division, but it was already one. Doesn't matter. It doesn't really hurt us. It allows us to have a single pipeline and stay in 4 dimensions as long as we can. So clipping, as we said, comes out very simply. Hidden surface removal will work both. Will work in the original space, but it works with these objects that I've distorted by these matrices. And finally, these are in the book, but here are the matrices that you get. They look a little complicated. Certainly the frustum is more complicated. But it's really, if you look at the form, it's got this sort of translation kind of component. Actually, this has the shear kind of component here. It has the scaling kind of on the diagonal. And you see that the perspective is much simpler because you don't have to do that shearing. So that's the mathematics behind all of this. And in a lot of ways, the derivation of this one, if you start from scratch, is probably about the hardest mathematical thing we do in the class. Okay, so next lectures we're going to move on and talk about some more things that come out of viewing, and I'll show you some examples, particularly with meshes.